Thanks very much for that. So I'm really pleased to be here, actually. We've had a very productive time doing work. I'm not a solar physicist, okay, I do all that other stuff, but I know very little about the sun. I'm a magnetospheric kind of a person, so it's been really nice to come here and learn some solar physics, and we've got some ideas how we can connect up solar stuff to space and magnetosphere, which is really nice, okay? So what I'm going to talk about is one of my interests at the moment, which is using ideas from the wider field of data and bringing them to our data. So I'm going to talk about that, and I'm going to talk about basically 3 different topics, depending on the time. The first one is looking at networks when you've got lots of samples, lots of stations. Okay. The second one is the sort of problem of what happens when you want to look across deep time. Well, no, it's deepish time, deep for us, to try and look at the data and what happens when the data is a bit dreadful and what do you do, and different things to do with that. So this is work done with bunch of students and a bunch of collaborators. So most of the stuff is student power, actually. So these are things that, you know, once you get your head around it, they are accessible techniques. So my hope is that even if you don't care about the magnetosphere, you'll get something out of the methods. And if you're interested in the methods, come and get me afterwards and I can share stuff, the details, because that's kind of what I'm aiming to do. Okay, so space weather. It's become a thing. It's a thing, as my students say. It's a thing. This is the UK National Risk Register, and you can see the little solar system there. Okay, so this is a kind of impact, reasonable impact, once every few years, kind of solar cycle-ish kind of thing. So this means the government now has to do something. They have to offer predictions, or they have to quantify risk now, because it's on the risk register. So therefore, there is a call for some of the science. And so what are the kind of risks? There are lots of different things that happen when you produce a solar flare. Obviously, you produce a nice shock, which can produce radio bursts, which can affect things on Earth. So you get solar radio bursts. So there's these prompt things. Solar radio bursts are prompt in the Earth. So this stuff will come in and fill up the ring current. So that's one of the things we're interested in. The other thing, because I disrupted this current that was going across the tail, it has to go somewhere. It's a current. So what it does, and this is what we're going to look at. So this is a picture again. The sun's over here. The field lines were just going, the current was just going across like this. So now I disrupt it, so it's going to go along the field lines. It's collisionless. It's going to hit the ionosphere, which is collisional. Current flows and comes back again. And this drives the aurora that you see in active times. It's very rough. There's a lot more detail, but that's kind of the rough thing. So if there's no big CME or anything coming, but you've just got the varying driver of the solar wind, you get substorms, and so you're loading the system up, and then it unloads through this instability. If you hit it with a big structure, in addition to all this stuff, if you're just going to squish the day side, basically, you're going to compress it, and that's a storm. And the storm, of course, will, depending on the sign of the magnetic field up front here, whether or not you get lots of reconnection. This is one of the problems of space weather. You don't know what it is till the last minute, right? If it's south, you really get a lot of connection in. It will pump particles into the ring current. So the sort of indices that people look at, there's loads of things you could look at. I'm just going to look at 2 kinds of measurements. One is in the auroral region. So I'm going to look at magnetometers in the auroral region to try and talk about this current. And the other one, and there's a thing called the AAA Index that I'll talk about, which goes back quite a long way in time, and I'll talk about other indices as well. The other one is the ring current. So the DST storm, okay, is a bunch of magnetometers in the equatorial region trying to tell you about the ring current. So these are the kind of data that people use to talk about these 2 key parts of the whole story. So that's what we're going to talk about, okay? Of course, we can't really predict all this stuff, okay? We can't predict when the flares are going to go pop. Once you see the structure, you can say something about it. You need to know the BZ to depend on how geoeffective it's going to be. Is it going to hit the Earth? Okay. Oh, so there's a big activity in terms of modelling all that and what happens when it hits the Earth. And in addition, this kind of substorm stuff, this thing goes unstable when it wants to. And so it's got a roughly 3-hour time scale, but, you know, it's a bit wobbly. So there's all that kind of thing. Okay. And this has all got really interesting, particularly for me. I've been mucking about this stuff for ages. But we're now, in space physics, we kind of crossed over from having hardly any data. So that drawing I showed was literally 1 or 2 satellites. They'd go around and they'd cross the boundaries. So you knew where all those plasma areas were, all those regions. 1 or 2. So you're trying to build that drawing out of just a few satellites. In a way, what we're trying to do with a network is avoid the similar problem you would get. You could instead kind of try and grid the data. I mean, obviously that's what people do if they've got a bunch of ground stations. This is an alternative to gridding. We can get stuff out without having to grid, so you don't have to introduce any correlations. That's really important. And so things can move around and you can still get stuff out. Okay, non-uniformity. You've got to make sure the stations are there. The varying conductivity. Okay, and so the key thing is deciding whether the things are connected or not as a function of time. And so we spent a lot of time on thinking about this. So first of all, the procedure. Okay, we've got a bunch of stations. We're going to do a windowed cross-correlation, canonical cross-correlation. So we remove the really, you know, we're going to pick a window, like a 2-hour window. It's minute data, so again, an hour would be nice, but then that's only for 60 samples. 2 hours is okay. 3 hours, well, that's, you know, lots of samples, but too slow. Nothing is ideal. So you have to remove the slow trend, do the canonical cross-correlation, okay? And then you'll have a matrix, so all the stations 1 to 100, 1 to 100 of cross-correlations. Now, if you're lucky in your problem, and they're all geographically in a line in space, you could stick with this, because and then you could watch things move around. You could actually, we tried this, we're making movies, but these stations are okay. So this threshold business, either you can model all those things I said, if you're really clever, or you know, I know how the sensitivities of everything is varying. I know it, great. But if you don't, then you ask the data, and that's what we do. So ask the data. We'll take a month around every event we're interested in. We'll take a month. We'll calculate the network. So for each station, we'll calculate on average how many connections they get as a function of the threshold. So you get a graph like this. You know, the fraction of connections against threshold. So as I raise the threshold, they're less likely to be connected in. And these are for different station pairs, and I'll draw a line across, say 0.4%, 0.5%, whatever I'm going to do. So I draw a line and say I'm going to read off the threshold I need to use such that that pair of stations on average is always 5%, 2%, whatever, connected in. And so they all get the same. And that's your one. You do it for every event because, of course, in the spring it's different to the summer or whatever. So it's intensive computationally, but the data tells you what to do. And that's one way of nailing it. So if you knew more, well, then you may do something else. The other thing, I won't dwell on it, but of course, for any complicated method like this, you want a surrogate. So what you do is you take the data, and I'm going to do something exciting with a network. And you might create a surrogate time series. So you Fourier transform it, shuffle the phase spectrum, transform it back. You now have a surrogate that has the same power spectrum but no phase information at all. Shove it through, and that will give you the network that could have happened by chance. So you can put a line on the plots to kind of say this is what would have happened by chance. So that's how you kind of get your baseline. You have to create a random phase surrogate. Okay, so let's do some science with it. Okay. You probably have this, I know you have this in solar physics, but we have the problem that people have been looking at substorms, you know, this business, forever, as long as I've been in the field, okay, and they've been arguing about exactly what this current pattern's been doing, because they've been looking at this chain and this satellite, and so I showed you this picture. This was the original picture, that you get, this is the tail, this end, the sun's up there. The current is flowing across the tail, remember, because it's a stretched out magnetic field, and then it's disrupted in the substorm, and so it has to divert into the aurora, and then you see a nice glowing aurora, and that's your substorm. But people have looked at this and said, well, we don't think it's this, maybe it's all this stuff. maybe there's 2 current systems, or more recently, maybe there's a whole lot of tiny little current systems, because you see these little bursty bulk flows in the tail. And so people just argue. So we're going to sort this out, or at least start to sort this out, okay? So this is quite an important point. You kind of need a bit of a physics hypothesis to test. You make this network, what do you do with it? So you have to put something in. So we're saying, well, we want to test this, so I'm going to divide up the spatial region into sections. Okay, so the middle part is where the aurora is, and I can get this for every event because I can measure this from the polar vis. So I have 2 boundaries here. The substorm starts where the little star is, and then I'm going to look at the network connections within these regions and across them, and that will tell me how the current's spreading and moving. So you have to have a kind of physics idea. I'm going to create a network to test that, and that's what we're doing, okay? Because there's a lot of information. So this is what these plots show. Time, the alpha, which is the number of connections within each region of the network or between, okay? And the colors, because it's cross-correlation, you've got lags. So you've got information, is it instantaneous or is it propagating? Okay, so there's a lot of information. And so if we look at these things, okay, I've got on the left is one event on its own, on the right, once I've done this, I can average over like 80 odd, which nobody's really done before. How do you average your drawing, right? Okay, and just as a kind of check. So what happens, you can see, I'll go through it quite quickly. First of all, in time, something happens in B, and this is what you expect. You get the disruption, and there it is in B. B turns up first, all sorts of different lags, okay? All the other things are coming a little bit later. Okay, then what happens, if I look at the connections going from B to A, they start to pop up. And the ones coming back tend to be more instantaneous. In other words, there's a propagation from B to A, but not back again, which is kind of what you expect. It's going one way. And then the other part, C only gets going much later. So now we've got dynamics. We didn't have that before, okay, for the thing. So we can now say, yeah, it could be that, but with the dynamics that I said, that this side goes first, then the other side. It could be that. It might be that, but this current system would have to get going before the other one does. They don't happen at the same time. It isn't that, because you've got long-range correlation. The idea was with this, people said, oh, well, they all add up to give you the big thing you saw, but this tells you they can't do that. So you can actually start to say it's this and it's not that, which is really good because people, otherwise you'd never end the discussion. So that's kind of the power of it. Okay, so that's the first thing, and half my time's gone. So I'm going to talk about the second thing now, which is going back in time. Okay. So we have in the solar wind, so we've got solar wind measurements, things on the Earth's surface, these indices that I talked about. One tells you about the auroral region. I'll go into it and explain. One about the ring current. Over the last sort of 5 solar cycles, we've got things like F10.7 a bit longer, and then some longer ones as well. And the problem I'm addressing now is the fact that, as you well know, every little solar cycle is different. So the amplitude is always different. And so if we're trying to talk about how active it's going to be in terms of space weather, you never know what's going to happen. So can we do something with that? Okay. And I want to do something without doing any modelling. Again, this is kind of the whole philosophy. There's nothing wrong with modelling, but it brings with it assumptions, okay? We know that these kinds of variables, particularly geomagnetic indices, but also in the solar wind, have different behaviours depending on the size of the fluctuation you're looking at. Okay, so if I look at them in distribution, the large events will not be from the same distribution as the small ones. So I'm going to allow for that possibility. But I'm not going to try and fit distributions, because the minute you do that, I've got to fit at least 2, and then I've got loads of free parameters, and it's so this is what you can do without having to fit anything. Okay. And so I'm going to use it to look at how things are changing in time between the cycles. So this is a really useful thing generally, okay? If you know I've got a multi-component thing and I don't know what to fit it with, or the thing you do before you fit, you might then do the fitting. So what are we going to look at? Okay, as I said, the AAA Index is something to tell you about the auroral activity. And so what they do, it's a really weird thing. They pick the station that shows the biggest deflection. And so this moves around, so it's an actual nightmare. Okay, but that's what you do. The number of stations is varying in time that you've got. So they fixed it and said, well, we're going to pick it from 8 to 12 or whatever. So you use these key stations. The one that's got the biggest deflection, you take your data from there. And then you subtract the kind of positive from the negative deflection to get AE, and this takes care of the background, okay? The DST is, I want to look at the ring current, so I take my 4 favourite stations in the equatorial region and I take an average. Okay, so these are the 2 things I'm going to look at. We've got them over these few solar cycles. Okay, just a quick reminder, everybody knows what PDF is. Some people, CDF, nod, shake your heads. Some nods, good. Okay, there's the likelihood of being less than some value. Survival function, I'm going to plot them, just swap it round, it's just 1 minus C. Why do that? Because if I plot that semi-log, I can see the tail. So it's nice. That's all it is, okay? It's the CDF really, but plotted so I can see the big guys. Okay. So here are some survival functions. So what I've done is pick out these guys. I came up with kind of an algorithm. I came up with several algorithms, or if it's a year and a half past the minimum and it's another year's worth or whatever, this kind of thing. So you come up with some algorithm for picking out where you think the maxima are, okay, and you vary it. And the colours are the data coming from these different maxima. And so these are the survival functions on semi-log, so you can see the tail. And of course, the point is they're different for each cycle. Particularly, you can see that like the last one was really quiet, the purple guy. So the DST was really small. I mean, that's small, 100, 200. That's not big storms, so hardly anything happened. Okay, and they all kind of flop around, and you'd really like to know what they are. But then it turns out, and I'll tell you where I got this from, if you pick a threshold, and it's different for these 2 quantities, we looked at lots of quantities, it's always different, and I'll tell you how I got it, okay? But if you just pick a threshold and say, I'll just take the stuff that exceeds the threshold, I'll get its mean, not the mean of the whole thing, just the big guys, and its standard deviation, and I rescale this axis, okay? So I rescale everything. They collapse. So it doesn't all collapse. The small guys do not collapse. It's a multi-component distribution. The small and the big guys behave differently. But these big guys collapse. So what we're saying is, this is quite handy. We're saying there's an underlying function for these PDF for the large events. And it just flaps up and down with the solar cycles. Okay. So if we could figure out, it's a bit difficult, but in principle, if we could get some estimate of what the next one's going to do, Scott has views, but you know, if you could get some, he's not here, it's all right. But you know, or if you can measure it, you know, from the first 6 months worth, maybe you could then say, well, this is what's going to happen for the rest of the maximum. So that might be quite handy. Once you've done this, then you can model it, okay? And that's what these things are. These are GPD fits, and then you can look at the 95% confidence and all this guff. So basically, you can get a parameter for this guy. You know, it will be different. These GPDs for each thing, AE, DST, whatever, it will have different GPD parameters, but you can get something. Okay, so fitting functions isn't that exciting. You know, you look up how to do it. What is interesting is how I got the threshold. Now, this is a little bit technical, so this is useful stuff, okay? I guarantee if you haven't seen this before, you might go away and think, oh, I'll do that. So what we're going to do is quantile plot. Some nods. Okay, so here's the idea. You take your CDFs, so the CDFs, and these may be, you know, cycle 22, cycle 23, or whatever maxima. So they're different, okay? And I want to know how different they are. So I draw a line at a quantile, maybe it's the 0.5 quantile, the median, or the 0.75, whatever. I draw a line across here, and I measure, that's kind of gone off the line, it's supposed to be there. I measure what X value that corresponds to, and then I plot X1 against X2. So this is used for people to test against distributions, by the way. So if I think my data's Gaussian, I get the data, I find its mean and standard deviation, I make Gaussian random numbers with the mean and standard deviation, and I plot this QQ plot for the Gaussian against the data, and if it fits on a y equals x line, then it satisfies your Gaussian. So people use it for that, but you can also use it to compare one bit of data with another to see if it's changed. So I can compare one solar cycle with the other. The other thing you can do, okay, if it fits on y equals x or x2 equals x1, then it's the same distribution. But if it's just kind of a straight line but kind of shoved off a bit, then it means it's the same, but it has a different mean and a standard deviation. So it's still the same function, but you just change those, okay? Because I just translated it, x2 is a, x1 plus b, okay? So this is really, I haven't had to model anything to get this out, which is really nice. Or you might find it fits for one range and not another, and that's what we're going to do now. You say, okay. It's actually, people draw them like this. It's actually easy to see what's going off if you plot x2 minus x1. That's what I'm going to plot. So now you get a straight line. If nothing's happening, if it hasn't changed at all, x2 is equal to x1, and it's a straight line. And now what I'm doing here is comparing the different solar maxima, okay? So, and the colours are so I pick one, the yellow guy, and I want to compare all the other ones to it. So that's why there's no yellow. And so this is how they change with the value of AE. So you can see like the red one is very much like the orange one. Doesn't change much. Whereas the green one is up here, the purpley one is down there because that's the quiet guy. But the key thing to get from this plot is you can see they kind of do one thing and then they go off and do another. So as the data is changing, as the system is responding to the different solar maxima, how it is changing is telling you where the two populations are, the physics. So the small guys respond in one way, the big ones respond in a different way, and that's where I put my threshold. It's actually telling you, you're using the physics to tell you, you know, how is my system responding to a very active maximum to a more quiet one? How does it change? And you can pick this out through that. So that's where this number comes from that I was showing you, and it's different for every quantity, and that's how you get it. So again, so you can divide. So if you know you've got two populations and you want to model them, it tells you where the break is in the two, which is really handy. Then you can go model them. Otherwise, you know, that's another free parameter. So that's quite a nice thing. Yeah.
These are only on the coloured parts of it?
Yeah, exactly. Oh, I changed it. Yeah, I tried. I can show you. I tried moving it around. It's within reason. It's not too sensitive. But yeah, I try moving it, and obviously that's what you do, and that's another way of getting uncertainties. You have to, pick something. So all this stuff the clock is based on where people believe the solar minimum to be is the start, and then you count so many years, and then you start, and then you wait so many years. Okay, so it's based, but yeah, I'm sure. Well, that's one of the things we've been doing here is coming up with a better way of doing that. So, yeah, that's the whole thing. Yeah. Okay, as I say, you can fit the distribution. We're just using the GPD as a fitting function. There's a whole story to do with extreme statistics. That's not what I'm talking about, just to flag that, but people can ask me about it. Okay, and so as I say, the other thing you notice here, well, you know that the last maximum was quiet, and you can see it in things like DST, which is telling you about these geomagnetic storms. Big storms, great storms, as people would talk about Quebec block, or whatever, would be in the sort of 400s, 500s, and DST, look, it's down in like the less than 100 or whatever. So it's pathetic, right? So the question is, what can we say statistically about these different solar cycles? But we've only got 5, which is no good. So I'm going to push it now and say, well, we'll try and get more solar cycles. Okay, and so now we start getting back to the really grungy data. So I'm going to talk about this thing called the AA Index. So if you remember, the problem is we've got to get rid of the background. And so one cunning scheme is that there is data going back, from 1868, where you've got 2 antipodal stations. So you've got one in the UK and you've got one in Australia. And so if we use them to cancel out the background field, because ones that because they're antipodal, then we can get an index. So this sounds like a great idea, but the problem is the data is this. You see these little pen charts? So basically, this AA index, it comes from something called the K index. So people took these charts. So, you imagine 3 hours worth. A little person goes along with a logarithmic scale on a bit of paper, holds it up to the chart and reads off a number 1 to 9. And you get a number 1 to 9 for each of these stations, and then there's a lot of kind of homogenizing and trying to make sure they're all in the same spot and this, that, and the other. You kind of form between these two by subtraction a number which ends up being in nanoteslas. Okay, so it's in nanoteslas, but it's this. But it gets us back to 1868. I know, this is life. Okay. And And I'm going to talk about it. I'm going to show you one more kind of plot, and you'll see why when I get to the end. And that's called a rank order plot. Some of you may have seen this. Okay, so just to remind you, the CDF is the likelihood of being less than X. The survival, I just flipped this round. This was just 1 minus C. The rank order plot, which people use when they don't even want to claim they're plotting a distribution, is to say, I take my data, I organize it in descending order, okay, or it could be ascending, but you order it, and I plot the value of the data against its rank. So the biggest guy would be the first rank, rank 1, the next biggest, the rank 2, and so on. So it's the kind of the same as the survival function, really. It's just been flipped round. So the key is, just as you would do with the CDF, if you were constructing a CDF, you would order your observations from smallest to largest, and C is just K over N. That's your empirical CDF. That's what this is telling you. So here is a survival function. This is the thing I showed you before. And here's the rank order plot. So there's the quiet guy. This is the size of the event now. And these are the more active cycles. And I'll show you why in a minute, why I want this rank order plot, because there's the results to do with it. Okay, so first of all, let's look at this AA index. So these are rank order plots, so they're like CDS. Okay, this is the DST that I showed you before. It looks okay. This is AA. So you see this horrible steppy behavior? And of course, this is this 1 to 9 business, okay? And it's logarithmic, so it's worse for the big ones, what we're interested in. There have been attempts to homogenize, which look like this, a bit better, but that steppiness, it's in there, unavoidably. But nevertheless, AA is doing what DST does roughly. The weak cycle is weak, the stronger ones are strong. So we ought to be able to kind of make a read across, which is what I want to do. Okay. So this AA is so rubbish, I can't just take the maximums. Normally, if you're trying to talk about a storm, like with DST, it goes negative. You take the biggest negative value, and it's a 400 nanotesla one or a 200 nanotesla one. Really, you want the rate of change, but, that's how you talk about the storms. Because the AA is so discretized, I can't do that. So instead, what I'm going to do is say, well, let's talk about something like, I'll take a month, and I'll ask for the top 0.5% or something that happened in that month and average it. So I'm trying to kind of find something that is a metric, a bit like DST, rather than just trying to find the maximum, which is no good. And then I've plotted here, I can then go for the last 5 cycles where I've got AA and DST together and look at them. So this is year, okay. The kind of blue one is the maximum. This is looking at annual, okay. I can look at monthly, I can look at annual. So if I look at annual, I can say, well, what's the annual minus maximum DST? How stormy was that year, okay? And then I can compare it with the same thing for AA, and they kind of follow each other. They're not the same, but they track each other. So I can check that over the last 5 solar cycles. And so I can kind of make a lookup table, which is what's going on here. I can plot the same data. This is the minus maximum DST because it goes negative. And this is the AA average top 5%. And I could do a regression line, something like that. So they roughly do the same thing. So I can, if people, they used to talk about DST numbers, you see. So I said, well, you're interested in a DST number, I can tell you what the kind of equivalent AA thing is. So when people talk about storms, a severe storm will be less than 250 there, or a great storm less than 500. And I can read them all across. And this plot is the sunspot number versus the AA. And now, instead of just the last 5, this is all the AA. So this is like, going back to 1860. And then I can say, well, I'm going to count how many years, these are all years, how many years were severe storm years and how many years were great storm in the last 150. So now I can get likelihoods. I can say, okay, in the last 150 years, in each year there was at least one great storm 4% of the time, and there was a severe one 28% of the time. So this is quite useful. But it's solar cycle averaged, and so we know that's not quite right, okay? But at least you can start to get some numbers out. But you can see, okay, so this is the plot of the AA index of the quantity I've been talking about, this 5.5% thing, okay? Sunspot numbers. Clearly, it's not constant, it's varying somehow with the solar cycle. So to say something about that, I'll do the same sort of thing. I'm going to say, okay, this is, again, instead of taking years, I'm taking solar maxima, solar minima, solar declining phases, as I did before, asking for the top 0.5% or the top 0.5% values of AA and averaging that, okay, and I can map that across to DST. So I can draw a line here. Everything above this line was a severe storm, and everything below was not, okay? And then the little colours are just, did it come from min, max, or declining phase? So you can see all the maxes and the declinings are kind of mixed up quite a bit because stuff happens in both. The minima are all kind of here, the blue guys, okay? And cycle 24, I put circles. So cycle 24 is quite unusual. It kind of sits in the same region as the minima, okay? So the chance of a severe storm in a quiet cycle like that is the same as it was in the last 15 solar minima now. So that now tells you something like if you get a quiet cycle, or you think you're going to get a quiet cycle, people are debating that. If you think it's going to be quiet, then it's telling you don't have to worry about, scary space weather events. So it takes a solar cycle prediction and turns it into a space weather one, which is kind of handy. Okay, so one last thing I want to talk about, really, and I'll probably stop. You've probably heard of the Carrington event. So obviously I'm going to try and put the Carrington event on this lot, okay? And there is a kind of an argument, I don't know how much people follow this here, but basically, although we don't have AA right back to the Carrington event, we do have the odd magnetometer. So Suratani got hold of one of these, and this is from his paper. And this comes out, if you look at the peak, at 1760, minus 1760. Remember I was saying they're like a few hundred? So this is huge. So, I mean, devastation, right? But then Cisco came along and said, well, hang on a minute, DST, the thing we've been talking about, DST, is an average quantity. It's not the peak value. So if you try and make an average of this, well, maybe it's more like 850, which is big, but not quite as scary. So the question is, how scary is the Carrington event, okay? So on my little plot I just showed, the 850 one would be kind of here. So it's outside the other ones, but not so far. The other one's up there somewhere, okay? So this is where I'm going to come back to the rank order plots. Okay. So these are all rank order plots. So there was some work, it's been going on for some time. Saul has proposed this idea of dragon kings. Okay, you may have heard of this, right? So I'm nodding. This is from his paper, because he's French, right? So this is Paris, and these are other he calls agglomerations, okay, French cities. So the idea here is that cities like Paris and London and New York are special. They're not the same as regular towns. And the reason is, of course, their drivers are different. I mean, the kind of, the financial side of things, the economics of it, what drives a city are different for these big global cities than they are just for the regular towns. And so if you look at a rank order plot, so this is the size, and and he's trying to fit it to a power law. So he's kind of done yeah, exactly. Sorry. Yeah, exactly. So he's already transformed the data for this plot. But the idea is that all the towns, if I rank order them, remember rank number 1 is the biggest, rank number 2 is the second biggest going along here. Okay. Will all lie along some kind of function. Remember this is a CDF really, so if they're all lying on a function, they're probably part of the same CDF, whereas Paris is up here and Paris is the Dragon King. So if we do the same thing for the Carrington event, this is my AA annual top 0.05% and 5% is to check it, averages on a semi-log plot. So this is the AA data, all lying nicely on a line. This is the Cisco estimate, the 850, if you average it. And so it's kind of nicely on the line there. I mean, it's bigger than the other ones, but it's the same population, whereas Suratani's up there. So you need different physics if you want to get this guy. And indeed, there's been a lot of excitement about this Carrington event. I was just at a meeting at AOGS recently, and I was in a session about these kinds of things. And people have been trying to reproduce them with the MHD models, of the magnetosphere. And to get up here, you have to really drive the magnetosphere into an exceptional circumstance, okay, to get that kind of number, which is consistent with what you're saying. It's exceptional. People have seen these big events, and they've You know, there are some famous ones that didn't hit the Earth, but they've seen them elsewhere in the, you know, satellites in other places in the solar system. And what made them so big was you'd have correlated extremes, that one CME would kind of clean out the solar system, and then the following ones could go really fast, and so they'd be more impactful. So you have correlated extremes. So you have some special circumstance to get up here. Okay, so this is important because if you're trying to get the likelihood of it, you know, if it's in this population, then I can then begin to think about modelling it, okay, and putting a number on it. Whereas here I've got to do something different. So that's why it's important to establish that. Right, there was one more thing I was going to show you. I spent the whole time talking about data, so I thought I would just mention this one slide, mention about bursts. We've been doing lots of stuff on bursts. I won't show a lot because I'm out of time really. But if you have data, what you really want is not the numbers necessarily, it's the time I spend above a threshold or the duration of this thing. Because if I'm a satellite in space and a flux rope moves over me, that would be the flux. I want to know about the flux rope, okay. And if you've got the data, if you know, in the solar wind we've got high resolution data, we can actually find the bursts. This other stuff like AA, there's no chance of coming. It's just not sampled enough. But if you've got high resolution samples, you can get this stuff directly. And that's one thing I wanted to show. Is this. So this is solar wind stuff. In the solar wind, we've got the data to do this, and we were looking at bursts. And if you look at the burst, you can get the distribution of the bursts, and you find, of course, it varies with the solar cycle, varies max, min, as you'd expect. But interestingly, if you plot the size, which is kind of the area of this thing, against duration, you find for different, you know, minima or maxima, we've got 2 solar cycles worth. They all kind of fit on a nice power law line. So what we're saying is that the size goes like the duration to some exponent, and the exponent is fairly stable. The different colours are just of changing the threshold, and you know, so it comes out 1.6 or something. Okay, different quantities, slightly different exponents. So density does this as well. This is magnetic field Poynting flux. So this is kind of interesting. It's a kind of a prediction in that if you know how big it is, you know how long it's likely to last. It's kind of handy. But I think what I think what it's telling us is that these structures have physical similarity. That a small flux rope is a scaled down version of a big one. Okay, and that's what is embedded in this. I haven't shown that yet, but I've got a suspicion that that's what's going on. So things like this can maybe have some kind of useful predictive power as well. So just to kind of finish, I've been talking kind of across, I think we're at an interesting philosophical juncture, because when I talk about these things, I get very different responses. Some people are like, well, where's the physics, you know, and some people, oh, that's interesting, and it's kind of quite a debated thing, because there's pros and cons all around, okay? So on one side, we have what we're calling data-driven discovery, which is I take like the networks. I take the network and I throw it at the data, and stuff comes out, you know, or there's testing a physical picture, which is, I know it's this, and I'm going to get the data that I can test my hypothesis. Okay, so if you're up this end, I might find something new, you know, that I didn't look for before, and I'm keeping my analysis open. Whatever patterns come out, I see them. The problem is I might find a really trivial or spurious correlation, and I spend ages faffing around and eventually found the rotation of the Earth or something, you know. So you say you can't just do this on its own. If you're over here, okay, well, I'm really in the business of confirming or refuting my picture. I know what it is. I'm going to go check it. Okay, so I'm going to focus on observations that do that, but I'm not going to look around it. Okay, and the problem then is confirmation bias, that it kind of disagrees with me, and I'm not going to look over there. So you don't want to just do that on its own either. You know, so basically, this kind of thing, finding something new, feeds into making new physical pictures. I find something I didn't expect, and now I've got to change my physical pictures. It also parameterizing things, which is what I did with the networks, and also to some extent the data from the solar cycle data. Once you parameterize, I can compare lots of them in a way that I couldn't before. If you're doing these event studies and trying to look, it does this or it does that, you're forever arguing about the event. So I can look at across lots and see, is it always the same, or maybe there's 2 kinds of things going on, and that's why people have been arguing, you know. On the other hand, and this is what I did with the networks, is I said, and to a certain extent with the other stuff as well, I said, I know there's at least two populations there, okay? I do use, if you need to use your physical insight or some information to kind of propose hypotheses that kind of feed into the data and analytics side of it, okay? So there's a kind of feedback that's important, otherwise it's just not going to work, okay? And so you end up, okay, I think to try and pull these things together, and my real message is really that if you can connect this side and this side, it forces clear hypotheses. And I think certainly in magnetospheric physics, this has been a problem. You know, you say, somebody says it's this, somebody says it's that. You know, we tried to make a table that tested all these different current models and then we found there was so much overlap in the predictions, it was actually quite hard to distinguish some of them, you know, so it pushes you to be really clear, and also null hypotheses. I mentioned about surrogates, you know, what does this look like happening by chance? Okay, and this might hopefully avoid these two very common problems, either being sidetracked into something which is spurious or falling into confirmation bias. So I'll stop there.